क्योंकि बोला जाना है 15 seconds का delay.
Yeah, this will need to be running for you though. I can meet earlier if you want.
हाँ ये और रहेगा मतलब जो रिकॉर्ड कर रहे हैं पहले तो स्ट्रीम बंद करो 1 मिनट मतलब छोड़ के स्ट्रीम बंद करो और ये तो मतलब ये देना पड़ता है क्लास से पहले बट अच्छा विजुअल अनिरुद्ध से लेना पड़ेगा आई थिंक वो सेम ही रूम में होता है ना जिस रूम में उसी रूम में भी अच्छा अरे मैं पूछ लूँगा जी अभी तो ठीक है
I'll probably be around. Okay. Probably just work or some other stuff.
I guess in which case, I'll let you know what time I get here. I guess I'll try to get here early. I'll try to get ready.
Maybe we should, yeah, I think we should try to be ready to write the document for facing towards it.
It's like 2 weeks to get this all sorted out.
Yeah, I think so. So I guess that means we should have like very good understanding of paper, I guess.
Yeah. Oh, that's Thanksgiving break.
Oh, yeah.
I don't know, maybe we'll have to do it, but we'll just see what we do first.
Yeah. Okay.
So, yeah, report to December 18th at 5.
Oh, just, yeah, that's right.
Yeah. And even actually, so I just had another thought that you don't have any time to do.
This is possible.
Okay. So today we're going to continue on the discussion for short optimization. I'm hoping that I can cover this topic today. If not, I'm going to use a little bit of time on Tuesday, next Tuesday, to finish this discussion on this. Then we are ready to discuss the last piece of relational database system, which is transaction, comparison control, and crash recovery. And just to remind you, I think both the projects and homework 4 are due next week, on Tuesday and Thursday respectively, right? Is that right? And what I'm going to do is I will release the solution for homework 4 once it's due, and give you a few days to review the solution. Then I will carry out a quiz for that, pretty much like what I have done for homework 1, 2, 3. So we will have a quiz for homework 4. This quiz will be a little bit longer time, simply because homework 4 covers a lot of stuff. So I will have a few more problems in the quiz, and of course give you a little bit longer time accordingly. And then we will have one more homework and one more quiz and one more project. Then we're done. Okay. Now let's look at so this is where we stopped last time. We talked about, okay, given input SQL query, you convert this to relational algebra representation to represent precisely and concisely what the input query means. And this is what we talk about from the beginning of the semester, that SQL is a very powerful way for users to specify what they want. It's what we call declarative language. So SQL is what we call declarative language. Declarative language, okay? And in contrast, relational algebra is what we call operational language. Each is kind of like operator, operates on things. And then you can represent this as a tree structure. This is what we call a query plan. And if you want to be more specific, it's a query plan tree, because it's always a tree structure. So the query optimizer overview is as follows. So your input, the input to the query optimizer is not SQL statement, by the way. The input to the core optimizer is a relational algebra expression, because you should have a parser that has done the job of converting your input SQL query to a relational algebra representation. So you have a tree of relational algebra operators, and some others with choice of algorithm for each operator. So by choice of algorithm for each operator, I mean the different ways of implementing the same operator we talk about. If you talk about join, for example, you can use one of the 5 or 6 algorithms we talk about for join, right? Hash join, block nested join, and so on and so forth. So, and each such operator may have potentially several different ways of implementing an operator. Okay? And each operator typically implemented using a pool interface, and that's basically the interface we talked about earlier, right? You have an initialization, you have a close, you have pool, get next, and so on and so forth, right? So when an operator calls this pool method, it will essentially call get next method from the operator down the pipeline. Okay, so that's how you kind of link up these operators. So two main issues in a core optimizer is for a given query, what plans are considered. In other words, if you have a plan like this, what are all the equivalent plans to this one? What are all the equivalent plans for this? You need to have a way to be able to generate all equivalent query plans. So that's question number 1. Question number 2, even if you are able to generate all possible plans, you still need to have a way to evaluate what's the cost for each single plan, right? Because it's impossible for you to just enumerate all plans and try to execute your query in each possible plan, then at the end of the day declare, oh, plan number 10 is the best. But then what's your point? You execute the same query 100 times, then just to claim plan 10 is the best, but you have already executed the same query 100 times. So you do need to have a way, an efficient way, this must be super efficient, to evaluate the cost of each plan. Why this has to be efficient? Because evaluating the cost of each plan takes time, so that gives you overhead. And if you have tons of plans to evaluate, even though the overhead for evaluating a single plan might be small, teeny tiny cost, but when you add up all the costs for evaluating all possible plans, that could still be a significant overhead. In the extreme case, that overhead itself might have already be more than the cost of executing a query using just one of the random plans. Then what's your point? You don't even need to evaluate, just take whatever plan you want and execute. Right? So this plan cost estimation must be super efficient. Another key observation, which is less obvious, is that in order to get really efficient cost estimation for a plan, we really need to do a compromise. We have to do a compromise. We have to compromise between accuracy and efficiency. Okay, and people do this all the time, right? So, for example, I decide to give out, I don't know, I want to give some tax benefit to a group of population that has the lowest average income. So I have, let's say I have hundreds of such groups, I want to decide which one I give the tax benefit to. So instead of calculating the average income for each group exactly, which might be costly, I can just do a rough estimation. As long as the ordering is pretty clear with the approximate answer, I will be able to make my decision already, right? So that's an example of accuracy and efficiency trade-off. So here is the same thing. To calculate the cost of a particular plan might be really expensive. To calculate this exactly might be quite expensive. But keep in mind, we don't really need to know the exact cost. If I know plan A is in the order of few thousand IOs, and plan B is in the order of few hundred IOs, I don't really need to know what is that few thousand, what is this few hundred. I can already make a decision which is more efficient, right? So that's the accuracy and efficiency trade-off. Ideally, if you can do both of this, if you can solve both problems exactly, meaning that you can enumerate through all possible plans, and for each possible plan you can calculate the cost exactly, then ideally you can find the best plan. However, in practice, that's just simply not possible, because you could have exponential number of possible plans, and even if you have a limited number of plans, to execute the exact cost of each plan might be quite expensive. So in reality, what Optimizer does is to do these two steps approximately and get rid of really bad plans. Then you are left with a few good plans you choose from. You are not really sure which will be the best, but you are pretty confident that this will be good enough. So you choose one of them to execute. So that's the overview. So to give you a quick recall of the iterator interface, that's what we talked about, I believe, 2 or 3 lectures back. We talked about each operator inside the database engine typically implements this iterator interface that has, among other things, 3 major components. One is an open method, a closed method. These 2 are basically to initialize the state and clean up stuff, right? And then you have this get next method that you have. And then in this plan tree structure, each operator will call the get next method of its preceding operators. Each operator will call the get next method of the preceding operator to continuously pull data or records from that operator, from the output of the operator. Okay. So this is an overview of Core Optimizer in relational database management system. And in fact, in many other systems, even things like NoSQL systems, if they try to build a query engine, SQL-like query engine on top of their data management system, they will have a Core Optimizer that are similar to this. So first of all, you're gonna have a query parser that takes SQL as input and generate an equivalent relational algebra expression. And then that equivalent relational algebra expression will be passed into this Core Optimizer. And the Core Optimizer has 2 main components, one for each of the questions I presented to you earlier. One is plan generator, the other is plan cost estimator. And then you do a mini kind of loop between the 2. You generate a plan, estimate its cost. If you're not comfortable enough, you generate yet another plan, estimate the cost until you feel this cost is pretty good enough. I don't want to spend more overhead in estimating more plans than you saw. And that plan will be your choice for executing this query. And you basically, the output of this box is a single plan that you have selected. And you push to the QRS executor. The QRS executor will simply execute the input query according to this particular plan.
Are statistics just metadata about the tables?
Yes. So let me come to this point, this part. In this process, because of what I said earlier, that both of these modules are doing an approximate job, right? They're not doing this exactly. So they need to have some data or information in order for them to do the approximation. If they have no data available to them at all, then your approximation will be of really bad quality. Right? For example, you want to calculate the average income for a group of people, but if I don't tell you any information regarding this group of people, how can you estimate? Your only estimation probably is from $0 to, I don't know, $1 million, right? That probably will be true, but it's not going to be anything useful, right? So we do need some data to make a high quality approximation. And what kind of data we typically use? Well, you interact with something called catalog manager. Every single database system, if you log into the database server, there will be a table that holds all such information, what we call the metadata table. And in the metadata table or metadata database, what kind of data it has? It has the schema information for all your tables. Schema information for all your tables. And some simple data summaries about your table, such as number of rows in that table, min and max value of a particular attribute, or a few attributes, and even possibly the distribution of one or more attributes from a given table. What do I mean by distribution? Well, frequency distribution, right? Or probability distribution function. So you can do that as a PDF, but really it's not really a PDF because the attribute is not a random variable, but essentially is you can argue this is like a frequency histogram. To give you an example, suppose this is the age attribute from a student table, and I want to know how many students in a particular age value group. So this will be frequency, and these are all the possible values for age. Let's say we start with 10, so on and so forth, right? And each will have a value, right? You draw. And maybe let's talk about university database. Then by the point of 20, then you have a sudden increase, right? You follow me? Of course, you immediately you can tell to capture this information exactly is very costly. It takes linear space, linear to the number of columns you have, not only linear to the number of rows, but linear to the number of columns. If you want to know the distribution for every single attribute. Furthermore, you need to maintain this, right? Whenever you have updates. So you have an update to the record, you need to come back and update this. So this is fairly expensive. So what people do is I'm gonna maintain some structure that can approximate this. So this curve looks like this. Maybe I can just one way to approximate this is I can just draw a line kind of like that. And remember, what's the cost of representing a line segment? X plus B. How many values do you need for knowing one segment? Huh? How many values do you need for one line segment? 2, 3, 4? Huh?
2 points and 4 values.
2
Points and 4 values.
2. Oh, you need this point.
Yes, 4 values.
So 4 values in 2 dimensions. Of course, typically you don't. There are many different ways to represent this. You don't have to remember the 2 endpoints. You can represent the angle of the line, and this. Then that should be good enough as well. But there are different. But boils down to some constant number essentially. And there's something called piecewise linear approximation. So what that means is, given a curve, I'm going to illustrate this in 2-dimensional space. So suppose you have a curve. Like this. To remember this curve exactly, you need linear space, linear to the number of points on the curve, right? Suppose the curve has this many points, you need to remember every single point to know the curve exactly, right? That obviously is very expensive. So what you do is you're gonna do a piecewise linear approximation. What do I mean by piecewise linear? Meaning that you're gonna approximate this curve with a collection of line segments. That's why it's called piecewise linear, because if you have a collection of line segments, every single element in your approximation is linear. It's a linear curve. Your line segment is a linear curve. So piecewise. So every single piece is linear. That's why it's called piecewise linear. So there are, of course, many ways to do a piecewise linear approximation. You can do something like this. One single line to approximate, but the approximate quality will be really bad. So you're going to use a little bit more information, right? So given this curve, the one kind of makes sense. Do you follow me? So that's what we call piecewise linear approximation. So this is one way you can reduce the cost of this. There's another way, which is what we call just a histogram. So what is a histogram? Suppose this is your data. Okay? Here, anyone looking at this will say, okay, hey, I can partition this information into two groups, this side and this side. Then I can represent all of this with a single value, let's say roughly here. So that from here to here, I represent all these values using a single bucket. This is what I call a bucket. You follow me? And then here I will represent all of this using a single bucket. That's another value. Then this becomes an optimization problem. One is, if I tell you I'm going to use B buckets, where do you draw the boundary lines of those B buckets? I can draw things like this. I can also draw a bucket like this. But that obviously going to be a bad bucket. Because if you draw a bucket like this, you're going to have these two curves and these guys. How do you use a single value to approximate all of them? No matter how you do it, you're going to have bad quality. So how do you draw the boundaries for B buckets? That's question number one. Question number two, even if you know the boundary, what will be the height of a given bucket? So this is what we call equal depth histogram. Versus there's also something called equal width histogram. Equal width is simple. In your domain, in given B buckets, you simply partition your domain equally into B buckets. And then you just find the best value for each bucket to approximate all the value in that bucket. Obviously, equal width is simple, but it's not going to be as effective because you ignore the knowledge about data distribution with your domain. Equal depth is better. How do we define equal depth? Well, the point is within, you're going to partition your domain into B buckets such that the summation of the variance for every single bucket is the smallest. How do I define variance within each bucket? Well, you can think about the height of the bucket is the average value, kind of like an approximation for the average of all the values in that bucket. Then each of them has a difference. To your bucket representation. You calculate the difference, sum the square up. That's the total variance you have for a particular configuration. And your overall goal is, given B buckets, find the optimal configuration that reduces this variance. Okay? So if I write the full, I can formula this. Suppose I have n values. Okay? I have n values. I want to approximate them using B buckets, where I define each bucket as follows. I define a bucket like so each bucket is defined by the starting point, end point, and the value for the bucket. You follow me? Of course, there is a clear constraint, which is the starting value of the next bucket is the end point of the preceding bucket. And what's your goal? Okay? So you want to find this B bucket such that this value is minimized.
So is Vj the average of all the values in the bucket?
Sorry?
Is Vj the sum of all
No,
of them?
no, widget is aligned to the bucket.
Right, so is it sum of all them?
No. This is widget. Widget is a variable you need to figure out. Okay? And this problem, this is a classic problem, right? This might show up in your interview question for Google or whatever. And you can solve, yeah. Go ahead. So this problem, there are two things going on with this problem. You need to figure out this configuration for the bucket, and for each bucket you need to figure out this value. Turn out that these two problems, luckily for us, are orthogonal to each other. Okay? Meaning that, regardless how you come up with your bucket configuration, once you know the bucket configuration, given a bucket, there is an optimal value Vi for that bucket. Once you know the Xi, Ei value, Vi is fixed. So you are basically reduced to the problem of finding out these configurations. Because once you know the configurations, how to calculate Vi for each bucket is independent from the other bucket and are fixed. That's how to calculate the Vi value, the optimal Vi value I'd like you to think about. Knowing that, can someone tell me how do you figure out the best optimal bucket configuration given B buckets?
Lloyd Max quantization.
Huh?
Lloyd Max quantization.
I actually don't know what that is.
Something we saw.
So, there might be
That's from
we may refer to the same thing, but there is more common terminology that I believe people use. And we may refer to exactly the same thing. So, anyone know how to solve this?
Do the recursion to try.
Recursion.
To try is the first.
The recursion space is huge.
But then you can use DP.
Okay. Use DP. Do you guys know what DP is? Dynamic programming, right? The point is, why DP helps solve this problem, right? To find the optimal B bucket configuration. The optimal B bucket configuration is equivalent to find the optimal B minus 1 bucket configuration, where you try this. What is the optimal? So suppose your domain value is n, right? From 1 to n, right? What you do is you try, okay, for this part, I use B minus 1 bucket. Then all the remaining, I use 1 bucket. Then you increase a little bit. For this, I use B minus 1 bucket. The rest is 1 bucket. Increase just one more step. This, I use B minus 1 bucket. The rest use 1 bucket. Then you have n such possible combinations. And then you choose the optimal one from that. That gives you B bucket configuration. And for each step, you use the optimal B minus 1 bucket for the first part, and only a single bucket for the remaining one. So this gives you, from B minus 1 to B, you need n steps. You need n cost. And basically, it's trivial. 1 bucket is trivial. So that's a DP. That's a simple DP formulation. Okay. So you use DP to solve this. Okay. So that's what we call histogram. And the problem with histogram, though, there's a problem with histogram. Histogram has this jump in boundary, right? It's not a smooth estimation. So recently, people start looking at smooth estimation, such as piecewise linear approximation, and even more advanced technique like kernel density estimate. And one more challenge is attribute values are often correlated. You follow me? They are often correlated. For example, this is the age value. You could also have another attribute called amount of time, let's say partying, right? Going to party. Right? So what do you expect this curve to be? Can this curve be something like this? Of course, this is this. I'm measuring this amount of time parking, and this actually is still age. Okay, still age. Can this be something like this? If you know that's your distribution for age, very unlikely, right? Very unlikely. What do I expect this to be? Well, I expect this to be then for 20, then you start going, then you kind of decrease. Hopefully, right? Once you get out of college, right? Hopefully you get back to normal. My point is there is a strong correlation between the two. If you represent them in separately, then you're gonna have trouble later on down the road. We will come back to this issue later on. But typically, most database systems they assume independence among attributes, even though that assumption doesn't really hold. But we have to live with something, right? We have to make some compromisation. If you don't assume independence among attributes, to represent the real distribution of your database is going to be really, really expensive because you may have a d-dimensional space if you have d attributes, and they may have correlations in any possible subspace. To capture this exactly is very expensive, as you can tell.
So the DBMS stores this information in the system catalog or the metatables or?
Yes, DBMS store. In fact, if you check Postgres SQL or MySQL, all these commercial databases, they will have the ability to create a histogram for any attribute of your choice or over any table. All you need to do is specify a value B. All you know is what this value B means. And they will physically do this using the EP formulation.
So internally, do they calculate that on the fly, or do they have?
Well, they calculate it periodically, maybe once a day or once a week, because to update this on the fly, it's going to be expensive.
So do you specify when you create the table, you could theoretically specify each attribute?
Not for all attributes, because to calculate this for all attributes, again, that's expensive because BP formulation is an n-squared algorithm. Right? If you have a million tables, you don't spend a million square for every single column, right? Even one column is already very costly.
So internally, does a typical DBMS use some kind of histogram data structure to track the distribution of?
Yeah, they do. I mean, for Q optimizer, you need to have histogram in order to. By the way, why you care about this? You may wonder. Because this is related to the thing I talked about last time called selectivity. I hope you guys can realize this by now, but why this? You may wonder how this is related to selectivity. Well, the point is, if I have a range where I ask from here to, for example, I ask from here to here, how many people have age between this value and this value? If I don't have histogram, I need to find. Remember, this represents this many records. That's not a single value. If this value is 10, that means 10 records. So you need to find 10 records, 5 records, and 8 records. You need to find this many records and calculate the count. But now what do you do? With the histogram, you don't. You just approximate. Let's say this value is 9, and there are 3 values in the range. I just estimate this roughly. And 7. And this can be done in constant time. Because you have this Barkey representation now become constant time. Okay? Okay, now enough for, yes?
One question I want to ask you. So what do you do about attributes like, for example, strings in how you quantify them?
Well, if your goal is to do a string search, right? Exact matching, then it's the same problem. You basically represent all possible values, then you can use histogram to represent that. But if you go to support selectivity estimation over approximate string matching, that becomes much harder. That's actually a very interesting question. I run out of time to talk about, but I can give you a quick some insight to it. Right? What you do is, so for example, how do you know? Maybe you right? How do you know these are essentially the same thing? Or spelling mistakes, things like well, I forgot to type U. Right? So how do you capture all of this? Well, there's a thing called qgrams. So you put a sliding window over this. And the point is, if the two strings are similar in spelling, the set of qgrams they will have a high similarity between the two sets. Now, how do you measure set similarity, by the way? How do you calculate the similarity between two sets?
Intersection of the union.
Okay, in order to do that, so this is one set, this is another set. So are they similar? Most likely not, because we only have this many common elements. Even this could be big, right? Let's say this could be 1 billion, but still they are not similar because the set itself is that much bigger. So how do you measure they are similar? Well, are these two sets similar? Even though this value may be just 100, remember this might be 1 billion, this might be 100, but you will still claim these two sets are similar, but not these two sets. So how do you capture this semantic? Well, that's what we do. You use this metric to calculate similarity between two sets. And then for string, you convert it to qgrams. So this is MI, IC, CR, RO, OS, S, and so on and so forth. This is LC, LE, EC, CT, and so on and so forth. So this string becomes sets. And so oftentimes string similarity match becomes set similarity problem. And how do you solve set similarity? That's beyond the scope of what I can discuss here. And then there is also the problem of how do you represent a set, a collection of sets, set of sets. Set of sets. So you have a database of sets. Each record is a set, it's a single set. And how do you represent those precisely, conceptually? Kind of like, do you have a notion of histogram for sets? So those are all interesting questions that I just don't have time to cover. But those are problems you wanna think about, right? When you go on and do advanced data analytics, those are issues you need to be aware of. Okay, now let's come back to the basics. Okay, let's solve this one first before you're trying to solve all these other things. So schema examples, I'm gonna use this particular schema for ease of discussion. I'm gonna write this down so that we don't have to come back to this slide all the time.
How often do you have to use statistics?
How do you have to use statistics? Well, for pure optimizer you have to use it, right? Pretty much. And for pure execution you don't. Because by the time you reach pure execution, you have a fixed plan to work with. So pretty much only pure optimizer will use statistics.
Now, how often do you update it?
How often you
You
update
get
it?
new data, you get
That's
less
a
data.
very good question. So later on, I'm going to do a demo of the one that we are currently working on, which is to address this very issue. And the traditional database approach is to calculate some kind of data summary of statistics about the data, and then maintain it over time. And the way they do that is periodically update this. Like every night at midnight, when you have no loads on your database, you update this. That sounds like a natural choice. But this works well if you have pretty modular workloads. Like every day you have similar kind of update patterns, so that your data distribution is not going to drift too much by a day of workload. So even if I haven't captured the latest workloads, the statistics is still going to be accurate to some degree. You follow me? So for example, the amount of partying time for college students is not going to change too much from today to tomorrow, right? Suddenly. I hope not, right? But there are other things that could change dramatically overnight, right? So how do you capture this? Well, one choice is to maintain live data summary as data updates coming in, but that's obviously very expensive. So you have to make a compromisation between the two. And this turned out to be a non-trivial problem, and that's one of the projects we are working on right now. Okay, schema for schema examples. So we have reserve and series. Each record is 4 bytes. I'm gonna have So by the way, these are statistic, part of your statistic as well, right? Number of pages, number of records, and so on and so forth. Okay, I will give you a motivating example to show you why cross-measure is actually important. You cannot ignore this. You cannot just bluntly take a query as input and execute as it is. That will be dumb if you do that. I need to convince you that, right? Maybe just take the query as it and execute it as it is not such a bad idea. Right? But I'm going to convince you that's not a good idea, actually. So I have this query over there, so I'm going to write setter, reserve, and so on and so forth, right? So I have one join between setters and reserve. Suppose I use page-oriented nested join over here. Then I do the selection and projection on the fly, meaning that for every join tuple I produce, I check the condition on the fly. Okay, that's my query plan. And what is the cost of this? For page-oriented nested loop join, the cost is for each page you need to scan the other page, scan the other table. You need to, by the end of the day, you scan the first table once, or right? And you always use the smaller one and output. Which one is smaller? This is smaller. So you're going to use setter as outer relation. So this cost will be that's not many IOs you have to do. What about those on the fly? Well, they do not generate any IO because you check this. You check them in your output buffer before you write to the disk. So that's not many IOs. Can we optimize this? Well, yes, we can. We can look at some alternative plans. For example, we can push down the selection. So remember, this is the base case, right? We start from here, which is about 500,000 IOs, pretty much 500,000 IOs. So IOs, and if you do the math, each IO, let's say, is 1 millisecond, typically, right? Random IO or sequential IO. Random IO is a little bit more expensive, but IO are typically in the order of milliseconds. Let's just say, and that gives you about, so you need about 500 seconds for the query. 500 seconds, which is about less than 10 minutes, 9 minutes, about 8 to 9 minutes. Well, what about another choice? Well, simply push down the selection. All you do is I push, there are 2 selection conditions here, let me push one of them down. And this keeps the same. Nothing changed. And what happens now, by the way? By the way, I do this selection on the fly. I do not do the selection and then dump the output to the disk and load them back in. So what do I mean by do this on the fly? Well, you're doing page-oriented nested join, right? And this setter is the outer relation, which means So the baseline argument is to read this in, then scan this through this second page buffer. Then load the next one in, do the same. Now if I do a selection, what do you expect to happen? When I load this in, I do the selection on the fly. This is my sigma operator, which is the selection. What do you expect to happen? Well, I have 10 rating values. By the way, if you do not have any statistics about a particular attribute, you assume uniform distribution because you know nothing about it. So select rating greater than 5 means that you are selecting about half of the records. Of course, this may not be true in practice because the distribution of rating value is not going to be uniform. Some people are going to be really good, very few people are going to be really bad, and most people are going to be in the middle. So you expect some kind of Gaussian curve. But let's say we don't know any knowledge about this at all, we assume uniform. So if we assume uniform distribution, what do you expect for this? Why don't I select on average half the records? And if you do this on the fly, what happens? When you scan through the first page, you're not going to fill in the entire buffer. You're going to fill in half of it. And don't start scanning, linear scan the other side. Move on to the second, and you expect to fill in the other half. Now you start scanning the other one. So what happens now? Every 2 pages, you scan the other table once. So what's the total cost? Instead of 500, it becomes 250 because you only need to do that many scans over this. But at the end of the day, you still need to scan all of this once. So it becomes this. So that's that. And timing-wise, this becomes about 4 minutes. So you cut by half. By simply pushing down one operator, you cut the cost by half.
How do you put 2 pages into one buffer slot?
Well, you are doing selection on the fly, so you are throwing away records that do not satisfy the condition. Okay? So you may wonder, okay, this is kind of like kids, right? When they do something, they get benefit, they will try to do exactly the same thing right away. So let's do just that. I push down on one side, I'm going to push down on the other side as well. So can someone, this is the thing I like about PDM, show the answer. Okay, let me tell you, the answer is the same, but can someone explain to me why it is the same? Why pushing down the other side doesn't help you? Me? You have to speak louder, right? People cannot hear you.
Okay. My first guess is
That's not louder. That's the same.
is ever both ID the same?
Huh?
Both ID.
Of
Yeah.
course not. You, like I said, if you don't know anything about the attribute value, you assume uniform distribution. Meaning when you select both ID equals 100, and I tell you there are 100 distinct boats, this on average will give you 1% selectivity. You see, you select only 1% of the records. So shouldn't you, by the same argument, shouldn't you cut the cost by
Because
100?
they are choosing seller ID, the same seller ID.
No. By the same argument, shouldn't we expect a reduction of 100 times? Why not, Victor?
Because we can fit all 100 boats into a page, right? So we don't.
No.
You still have to scan all,
Right.
it's on the outer, but you still have to scan all the records.
Totally. What Eric says is to the point, right? Yes, you're doing the selection of code ID to 100 on the fly, and yes, you're going to reduce the number of qualifying reserve record by 100-fold. However, you're doing this on the fly, meaning that for every 2 pages of sailors, you still need to scan all of them once. You may wonder, that cannot be right. I got to be benefiting from this. I need to have some saving, right? Well, the saving is, yes, IO-wise we have no saving, but CPU have you save big. You save big time. Roughly every 100 pages will be reduced to just 1 page. So you don't have to do this in-memory nested loop that often. You only do this in-memory nested loop every 100 pages also. However, in IO-wise, you still need to scan all of them. And you still need to scan all of them for every 2 pages on this side. So the total cost stays the same, IO-wise.
So if we know that there's only 100 books that match, why can't we just load those all into a buffer and then just scan over that buffer and match over that buffer?
Well, because you have to go with what the plan says, right? You're using page oriented network join. You have to go with what the plan does, right? You cannot just.
Yeah, I guess I'm trying to prematurely up.
Okay, let's continue on. This time I'm not going to show you the answer. Anyway. All right, so let's do this one. This one is the same thing. So is it the same? Oh, it's the same. So okay, I'll show you the answer, but you need to explain to me what it means. Okay. Now,
The other one has better selectivity.
yes. So flip the order. Push down selection 100, but now use the reserve as alter. Now what happens? So the picture becomes this. Every 100 pages become a single page, and for every one such page, you need to scan the series. So what will be the cost? Well, you have 1,000 pages here, but only every 100 of them you need to do a scan of this, which is 500 pages. But by the end of the day, you have to read all the pages from here, so that's what we get. And this is roughly 6,000 IO. Now we'll translate to time. 6,000 IO is what? This is not minutes anymore. So from 8 minutes to 6 seconds. So your boss will not care. You tell him, oh, you know what? I can do your query from 9 minutes to 4 minutes. If I will give you a bag of candy, he say, oh, good job. But once you go out of office, he said, who cares, man? But the next time you come in, you say, hey, boss, I can reduce the cost from 8 minutes to 6 seconds. I guess no matter who that boss is, he or she must show some care. In this case, right? I mean, it's like, come on. And from another thing is, people always confused about this. Like, okay, you reduce your cost. Let's say you reduce your cost from 10 seconds to 1 second. Does it matter? For a single user point of view, maybe this doesn't matter. I wait 10 seconds versus waiting 1 second. May not matter that much. But suppose you are Amazon.com, and assuming that let's use a very simplified model, which is I make $1 at Amazon.com. I make $1 on every query people do on my website on average. You may wonder why that matters. Well, given 1 minute. Suppose you execute all queries sequentially, right? Which is, of course, not the case, but let's use this simple argument. If you answer each query in 10 seconds, how many queries you can answer? 6 queries. Meaning that you profit at $6. If you can answer each query 1 second, how many queries you can answer? Meaning your profit is $60. And that's why your boss cares. Your boss doesn't care because of this. Your boss doesn't care because of this. Your boss cares because of this. Because they have to care, right? I mean, when you have same time, your profit increased by tenfold. I mean, I cannot imagine anyone who doesn't care about this. Right? That's why this is important stuff, right? I mean, you can, by simply doing one push down, you can do it. But is this good enough? Well, we can do. This is the one, right? So we continue on. Now I push down both selection operators. You may say, wait a minute, you just said pushing down both doesn't help. Well, I'm going to change the game a little bit. For the pushing down of the selection, on the other hand, on the other side, I don't do the selection on the fly. I will do the selection, then dump to disk and read it back in. And why this helps? Okay. So let's see what's going on. This side stay the same. Every 100 becomes just 1. Every 100 page becomes just 1. But what about this side? Well, I'm going to read all of them, but not into this buffer. What I'm going to do is write back to the disk. So the 500 pages become half, 250 pages. And only after that, I will start doing this, which is every 100 pages I scan these ones, which is 250. So what will be your cost? This step, from here to here, is 500 read and write. What about this step? Well, for every 100 pages I need to scan, but not 500 pages, but only 250 pages. And that's how you get that value. Yeah, it is the same. How is the difference? So it's Sailor. How many pages Sailor have? Maybe I confuse the.
You have to read in the entire.
Oh, yeah. You have to. By the end of the day, you need to read this once. So there's another 1,000 IO over there. Yeah. Another 1,000.
So I think this kind of brings up a point that this is a strategy that you use. They use 10 tables all the time. If you want to.
No. Don't make that 10. I'm not done yet. Okay. Actually, I will go against using timetable all the time. That's a really bad idea. It shows you some saving here, but it doesn't mean this will be always what you are. We will continue on. Right? So, next, now you see how this works. Let me try to flip the order once more. Flip the 2 again. Okay. What will be the I/O cost? Well, read this in, that's 1,000 IOs. Write it back to disk, because selectivity 1% become only 10 IOs. And then for every 250 pages, for every 2 pages, I need to scan this 10 pages. Because the unit page has to be drawn. So that's 250 scans over 10 pages you have to do. And by the end of the day, when you finish scanning this, you need to read this once, which is 500 IOs. So that's the total cost. I mean, you save a little bit, but not too much. Let's continue on. Now, so far in our discussion, remember, all we have done are simple stuff, right? We're not using rocket science. All we have done is pushing down the selection operator and flip the order. We didn't even try fancier technique yet, like hybrid hashing, two-phase hashing, merge sort, refinement, tunement, all that stuff. We didn't even use any weapons, essentially. We just kind of play with this just a little bit. You get so much saving. What about start using those really even more sophisticated techniques? Well, let's see. Well, what I'm going to do now is I'm going to scan and write to disk on both ends. Then I do a sort merge join. By doing a sort merge join, you need to be careful here because there are 2 versions of this algorithm. One is the basic version, which is sort, then join. The other is the refinement we talked about, which is do the pass 0 of the sort on each table, and then on the pass 1 of the merge phase, you do the merge and join together. If one condition holds, which is that condition? The square root size of the bigger table must be smaller than your buffer size. Well, let's check. Okay, let's see what's the cost. Okay, I'll do this. Well, first of all, there will be costs like this up front. This is to just read and produce the timetable by applying the selection operator. And then you need to right, that's the cost. And this is the final step, the linear cost. But you need to do this. The question is, what is this? For 5 buffers, what's the cost of this? This is lead, right? For 5 buffers, this one you can, in the path 0, you reduce to 2 rounds. So you only need 2 paths. So this will be 2 times 2 times 10. What about this? 250 reduced to 50 rounds. 50 rounds reduced to, and you're merging 4 of them. 50 rounds reduced to 13 rounds. A 13 round reduced to, so 250, 50, 13 to 4, 4 rounds, and you're done. 1 pass, 2 pass, 3. So you need 3 passes over here. So the cost of this will be yeah, that's essentially what's on the slide. By the way, you should be able to calculate this as fast as I do, right? And it's not, if you follow what I'm doing, it's actually not that hard. You need to understand what these values mean. In path 0, you produce a round of 5 pages. That's why it's 50 rounds. And then in all subsequent paths, you're merging 4 rounds at a time. So 50 rounds becomes 13 rounds because it takes the ceiling of that. Then 13 rounds becomes 4 rounds. 4 rounds merged down.
So you only need to count passes because you're always...
Because each pass you do linear I/O times 2. So it's actually very easy to calculate this. All right? You don't have to plug in that log, whatever formula. You can if you want to, but you don't have to.
What is it, 260?
At the end of the day, you need to do that this thing, which is linear to the sum of the 2, n plus n. Okay?
Then why is the previous becomes 1,000 pages to write down?
No, the 260 is explained right here, right? The merge, this is 10 plus 252. The 260 equals 10 plus 250.
So we applied this selection to the relations before we did the merge. So we eliminated the records that don't satisfy the selection.
Okay, this is the step. Step 1, step 2, step 3, step 4. We can take this offline if you still have doubt. So this becomes 3,000 some IOs. What about the refinement of external merge store join? Can we use that? Well, you can quickly check, right? This is roughly 15. 16. Oh yeah, 20. 15. Yeah. 15 is 16. 15 is 175. So 16 is 196. So roughly 16 something. Now this is the other figure. In fact, do you need to check the other one? No, you don't. The bigger one needs to fit, right? So you cannot use this. Well, what about? Okay. What about? I should cut this, but we're almost done, right? What about block nested loop join? For block nested loop join, which one you should use as alter relation? Smaller one or bigger one? Well, you can do the math, right? It's small. Then divide by 2 times 2. So obviously you should use the smaller one as alter because the other terms are the same. So which is the smaller? Well, if you do this, then the reserve becomes smaller rather than the saver. Right? So your cost will be or if you don't do that, your cost is simply right? And you can also push, in addition to push down the selection operator, you can also push down the projection operator. But you pushing down the projection operator, you need to be a little bit careful. You cannot just, in this case, if you put that seller name all the way down, you're not going to do anything. Not be able to do anything. You need to put that out, the seller name and the attribute used for the join and all the attributes involved in the selection. But it does help because while you're doing the selection and projection, not only this will be reduced to 250, this will be a further reduction of some factor. I don't know what that factor is. Why? Because that factor depends on the attribute size of each attribute you have in your schema. And that's actually a complicated issue to estimate because it depends on, if you have fixed length record, this is easy. If you have variable length record, this again becomes something not easy to estimate.
Would it always be in your best interest to do the projection?
Well, if you are pushing down the selection, yes, it will be the best interest for you to do projection because there are no additional costs. You do both selection and projection on the fly anyway. Right? However, there are cases where you not necessarily want to do this. I'll give you an example. Suppose you have a unclassed index on your selection attribute. So if we only push down the selection, you can do the selection using the index alone without actually looking at the record. But if you push down the projection, you have to retrieve the record and it's unclassed index. That's but you may wonder, you need to retrieve those attribute values anyway, but the point is maybe not. Maybe you use the secondary index, unclassed index, to find all the necessary IDs, record IDs from this table, from that table. This reduces your join cost dramatically. And then you join them and your join size becomes super small. And then for the join size, yes, I only have the record IDs in the join, but only at this point I go and fetch each record. Still much cheaper than pushing down the projection in the first place. However, if you have a classed index, then why not? So it all depends. So this is actually not trivial.
Seems like in that case, though, too, it would depend on like your buffer size, because even if you had a cluster index, it may be too costly as far as space goes to read the entire record.
Yeah, even if you have a buffer index, reading records in the range is still going to be more expensive than reading data entries in the range. So in that case, still depends, but chances are you're not going to lose too much by reading records and reading entries in that case, because your buffer typically is big and you're doing sequential IOs, and operating system and disk often do prefetching anyway. So, typically you're okay, but of course, you never know, right? It's system, right? Okay, now, what about index that's withdrawn? So I'm going to do index that's withdrawn. And suppose I have a cluster index on board ID. Okay, I have a class index on board ID. So let's go through this example together. By the way, in the previous example, can I use the hash join? Can I use hash join? Let me write it down. Okay? Can I use hash? Me? I'm going to ask you again.
Is the other one also equality structure?
No, I'm not asking this. I'm asking hash join.
Hash join?
Yes.
I think hash join could only be applied to if they are equalities.
It is the equality, right? SID equal to SID. I mean, answer is, of course you can use hash join, right? What is the cost of the hash join, I guess? Someone want to help?
Well, actually, I'm confused now why we said we could use sort and merge term before, because when we did the square root, we got 16.
No, you cannot do the refinement of sort merge. You have to do the sort. But
Okay.
you cannot do sort merge.
Okay.
The refinement of order of the sort merge. You cannot.
But here you can, because
Yes.
the square root of 10 is...
Yes. Square root 10 is.
So it's
Okay. Alright. So I see quite a few puzzle physics. You guys, when we move on in lectures, I can move on. You have to stay back just a little bit and pick up, then move on, right? I can talk, then move on. You need to stay a little bit behind me and pick it up and move on. You cannot just, Feifei move on, I move on too. But at the end of the day, I move on with things still in my mind. You move on, you don't remember what I said, that was the point. Okay? So it's like I move on with $1,000 cash in my hand, and you move on, I keep dropping $10 bill and you didn't pick them up. You move on with $0 in the end too, so that's no point. Okay? So you need to remember what I said. Okay. Now back to the index method job. Okay?
Wouldn't that be 3 times 250 plus...
Oh, yes, you're right.
I'm picking up that $10.
All right, so let's move on. I think this is the last one. Now we have index. We have index. So far we haven't talked about index, right? So let's talk about index. Let's say we have a cluster index on board ID. And the selectivity is so what is my selectivity in this case? Well, I believe for the reserve table I have 1,000 pages and I have 100 records per page, right? I think that's what I said. And so in total this gives you this many tables. But since you are doing a selection on board ID with the selectivity of roughly 1/100, because assuming this uniform distribution, this gives you roughly 1,000 records. Assuming you have a cluster index, what is the cost to retrieve 1,000 records from a cluster index? Well, each page is going to have 100 records. 1,000 records are going to span roughly 10 pages plus, maybe some 1, 2, or 4, depending on how to trade off, depending on how many buckets you have in your hash. But roughly, let's say just 10 pages. And in this case, I don't have to materialize this selection. I can do this on the fly because I have index. So I don't have to really do 1,000 plus. I don't do this. I don't do this 10. I use the index to get this 10 pages on the fly. You follow me? And because here is another knowledge you can leverage on. You are drawing the two tables on sealer ID. What does it tell you? Well, sealer ID is the key on sealers. Which means what? Which means you're only going to have one matching record from sealers. Why that matters? Well, it matters because now you don't care whether it's cluster or unclustered. When you know there's only one matching record, cluster, uncluster, they're all the same. That's the significance of this. Because if you have only one matching record, whether it's cluster or unclustered, doesn't matter. You go down the tree, you fetch the record. So what will be the cost? Let's assuming I have a hash index on the sale ID from the sellers table. This becomes really efficient because all you're doing is you get this 1,000 tuples. You get the 1,000 tuples, right? And for each tuple you pay roughly, let's assuming hash index is 80% filled. Which means you roughly retrieving one record costs you about 1.2 IOs on average. With that, we talked about this way back, I have this assumption. Then on average, you can estimate a hash index, the IO cost is between 1 and 2, let's say 1.2. So for each tuple, you pay 1.2 IOs to find the matching sealer record using this hash index. And of course, to find this 1,000 tuples, you need to pay how many IOs? 10 IOs. Using that cluster index on ODI. So the total cost is what? Is 1,200 IOs. So we go from 500,000 to 1,200 IO is what? 1.2 seconds. So you go from 8 to 9 minutes to 1.2 seconds. What about pushing down the selection operator here? The rating greater than 5. Does it help? Well, not only it doesn't help, it actually makes the matter worse if you try to push down that in this case. You follow me? Because if you push down that, your cost of doing that, depending on whether you have index or not, but you have to rate the entire seller table at least once. If you don't have index, right? If you have index, maybe you can do this a little bit more efficiently, but the output size has to be 250 pages at least, because you have to pay this cost anyway. And since you have a hash index on seller ID, there's no sense for you to do the selection on ratings first. You just do the join directly. So this gives you another clue, which is it's not always the case pushing down operator helps you. You may wonder, oh, seems that all the examples so far suggest that in co-optimizer you should simply push down the operator whenever you can. No, not always. All right.
We wouldn't want to do sailor. We wouldn't want to like switch it and there's a selectivity for.
If you switch, it really depends on whether you have an index on that sailor selection condition or not. You know what I'm saying? Because if you don't push down that selection, if you switch, what you're looking at is 500 pages and 80 records per page. This many records, and for each of this, you pay the cost of retrieving the matching reserve cost tuple from the reserve. This actually is pretty expensive. So what is needed? So I don't have to. By now, I don't have to motivate you why we need optimization. Clearly, we need this guy. Right? The question is, what is needed for optimization? If you know database, if you follow the course along the way and you understand everything I said, you can pretty much see how this optimizer works, right? But the question is, how do you translate this into a computer algorithm that can do this automatically without human input? That's not going to be trivial, right? Because the query example I use is a really simple selection join, right? We haven't even touched things on goodbye. We haven't touched things like nested block, like in exists, not in, and except, and all that stuff. And what about those guys? What about, and we haven't touched on things join over multiple tables. Currently, we only look at join over 2 tables. Why join over multiple tables is hard? Well, join with 2 tables, you can see the order, which is in there matters a lot. What about join with K tables? What are the possible ordering you have.
K factorial.
It's a K permutation. It's a permutation of K. And in addition to that, you have the choice of, that's just the ordering. In addition to that, you have the choice of whether you do the selection on the first one and write it to disk or not. Do the selection on the second one, push on to disk or not. And do the selection on both first and second and push to the disk or not. Think about the combinations. And you become dizzy after thinking of a while, right? The combination is just endless.
Is it even feasible?
Yes, that's a good question. We will come back. We will come to that. Whether is this even feasible? At some point, you're gonna ask this question: Is this even feasible to enumerate all possible plans? The answer is no. The answer is no. We're gonna somehow cut down the search space somehow. Okay. What is needed for? Well, I think we have covered enough today. I don't want to kind of burden you too much. So why don't we just call it a day and stop here?